This is a digital circuit class. And we're in chapter 3. And this is day 2. And all things being equal, we should finish chapter 3 today. So the first thing we'll talk about is circuits that will enable and disable something. And I tell you what page I'm on, but I'm not open to that page, so it won't matter. All right, so if I go and I have some signal, and it's a digital signal coming into an AND gate, and I've got a switch, so I'll do it this way. I got a switch on the AND gate that can either be 1 or 0. And I take that switch, and I'm in the one place. So I got it hooked up to the one place. Then whatever my signal is, my signal out's going to be the same. And it would be cool if I had a digital signal going in and out. So whatever my input signal is, my output signal is going to be the same. If I take that switch and I put it to 0, then whatever the input signal is, the output signal is going to be 0. We call that I've disabled the circuit, whatever it is. Or I enabled the circuit, depending on what switch, what position I'm in. I can do the same thing with an OR gate. So I can take an OR gate, and I can have some signal coming into the OR gate. And I can have some switch that goes to a 1 or goes to a 0. And if I'm in the 1 position, what I end up getting is a 1 out. So I have disabled the circuit. I'm not seeing the signal anymore. If I go and put a 0 in that OR gate, then I get the signal out. So I've enabled the circuit.
No, if it stayed on 1 and it's an OR, couldn't it be enabled the whole time? Wouldn't it be on the whole time?
That's right. That's why it's a 1 the whole time. I'm not seeing the signal. I get a logic 1 out. Yeah. Yeah, the AND gate has to be at the 1 in order to see the signal out, and the OR gate's got to be at 0 in order to see the signal out.
Oh, to see the signal.
Yeah, to see the signal out, because that's what I'm enabling. I'm disabling the signal, not something else. All right, well, I missed that last time around for some reason. I don't know why. Okay, so we have inverters. They look like that. They have math that go A, X, and X is equal to not A. And they have a truth table, AX 0, 1, 1, 0. And we have buffers. And they look like that. And we have an A in and we have an X out. And A is going to be equal to, X is going to be equal to A. And we have a truth table. 0 gives me 0, 1 gives me 1. And we have AND gates. And they look like that. We have an A, we have a B, we have an output that's an X, and we say X is equal to A and B. Even though it looks like they're multiplying, we still say A and B. And then they have a truth table, ABX 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. Notice that my truth table is counting in binary. So if I had a 3 input AND, 1, 2, 3 input AND, I'd have a truth table and it'd go A, B, C, X, A, B, C, X, and X would be A and B and C. And when we want all possibilities, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And we get an output of 0, 0, 0, 0, 0, 0, 0, 1. And then we have OR gates, and OR gates look like that. And we have an A, B, and an output X, and the output X is could be written as A or B. We pronounce that A or B. The algebra we're using is Boolean Algebra, which it comes later in the book, that word comes in. But George Boolean and I both went to school together. He died around 1820 or so. Really? They have a truth table, A, B, X, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. George went and made Boolean algebra up in 1820. Now, at the time, there was a whole lot of people making different algebras up. Math people were just making up a different algebra. So today, there's modern algebra, there's the 9th grade algebra you did, there's the normal math that we call algebra. But before TV and radio, we had plenty of time to think about those things. Well, George's Boolean algebra stayed in a book on the bookshelf for another 100 years. It wasn't until we got to tube technologies where we could make AND gates and OR gates and other such things with tubes that we actually started using it again. We had never used it for anything. He made it up and we never used it again. Now we can use it because we have something to do. Okay, we have NANDs. And they look like that, A, B, X. X would be A and B inverted. So the bar above means I'm inverting it. Inverting it meaning if it's a 1, it's a 0, it's a 0, it's a 1. I have a truth table A, B, X, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. And I've got a NOR gate. Looks like that. A, B, X. And we say it's A or B not. There's implied parentheses that we don't write, sitting right there. So as soon as you put that not bar above the A or B, you're implying that it is going over the whole thing that's underneath. So that's a case where we have implied parentheses. We have a truth table, A, B, X.
Real fast,
No, I'm not. This is all review. 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0. There we go. Bunch of zeros. What do you want me to go back to?
Just the NOR, the truth table for NOR.
Oh, that's it. Yeah. Oh, yeah, look on page 95. It's there. Good plan. Good plan, yeah. Okay. So what's left? That's about all there is.
We just got to finish the rest of the homework.
Yeah, we just have to do the rest of the homework. Now, the other issue is I got these pretty gates, right? So I got this AND, and I got this inverter, and I've got this OR gate. But the fact of the matter is, I don't have anything. I'm going to have an IC, an integrated circuit, 7408, so that I can have 1, 2, 3, 4 ands. So if I want an and, I'm going to have to take 4 of them. I don't have a choice because it's just too expensive to do something else. Pin 7 will be grounded. Pin 14 will go to 5 volts for voltage. without the voltage, without the ground, the chip's not going to work. An input is going to float, and it's going to float high. So if you want an input to be 0, you're going to have it grounded. If you don't, then it's going to float high, and it's going to mess up your logic, and that's not good. Okay, so on page 93, there's a 7404, the 7402, the 7401, 7400, and yeah, you can memorize them all if you want to, but the fact of the matter is the front cover of your book has everything you're going to need as far as what IC chips we're using, and when it's come time to look for one, unless it's really weird, it's going to be just there ready to be used. Okay, questions about that? Anybody remember what question we left off on?
322.
322. So we're going to start with 325. Now, how many more times do I have to review what I just reviewed? 17? Yeah, okay. That's right. That's really the right answer. As many as it takes. You know, if it takes me the rest of my natural life, you will know what an inverter is. Won't that be good? All right, so I'm turning the page, 102, and it says we have a figure below. Write the Boolean equation for x. All right, so I got this equation below. We have an a, we have an x, and we want to write the Boolean equation for x, a naught. So I did that. It can also be a naught. It could be that way. So that apostrophe thingy in Boolean algebra means the same thing as the bar thingy. So think about, I'm typing something into a computer. How do I get a bar over that A? What keystrokes do I get to use to get the bar over the A? And you say, yeah, I'm sure there's some Control Alt Shift 14 or something that it's going to do it, but that's hard to do. But this guy, a with just an apostrophe, that's easy to enter into the computer. So in multisim, if you want an A naught, you'd use this, because how are you going to get the A bar? But in writing it and doing your homework, you use the A bar because that's easy to do with your pen.
No, like how above the bar would cover all the letters. Does there need to be an apostrophe after each letter?
Yes. No. That would be different. So if I have A, B, C bar, then it'd be A, B, C knotted, A, B, C knotted. That's what we're talking about. So I would write that as A, B, C, like that, with parentheses. We're not there yet. A, B, C knotted is not the same as A naught, B naught, C naught. Okay, those are not the same in Boolean algebra, but we don't get to the nuances of Boolean algebra until chapter 4. Maybe. No, probably chapter 5, because we skipped chapter 4. No, maybe not even there. But some place we'll learn, and you don't really want to know, but well, because you asked, A, B, C knotted is the same as A naught or B naught or C naught. Those two are the same thing. And De Morgan's theorem tells us that, and we get that from De Morgan's theorem. But don't let that bother your little mind today. We'll just erase it so you don't have to let it bother your little mind today. Why that is. But if we look at A naught, A, B, C naughted. And we look at the truth, we look at this guy here, and that's that truth table, right? Then we find 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, all the way down until we get to 1, 1, 1, 1, and then we get, well, too many ones. We'd get a 0 there, right? But A naught and B naught and C naught would have a different truth table associated with it. And I'm not going to write it down, but you can take my word for it. Back to the problem we're doing. What is x if A is 1? All right, so back up here, there's our answer. That's our answer. And if A is 1, x is 0. That's the other part of the answer. Who assigned that anyway? That was way too easy. 28. For the figure below, write the Boolean equation for x and y and build a truth table for each. All right, that's what you want me to do. That's what I'm going to do. No, 3-20. It can't be hard yet. See, and that's, so I'm looking at this and saying, wait a minute, you got to be kidding me. You're asking me such a fundamentally simple thing? All right. X, D, C. C, D, Y. All right, so truth table A, B, X. 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0. All right, next guy, C, D, Y. And it's the same stupid circuit, so of course it's going to be the same thing. 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay, so I did that. 828. 328. Why don't we do...
Wait, that was just it?
that? Yeah, I know. Isn't it pathetic? Oh, wait a minute. It says write the Boolean equation, so it's not it. So I still have to say x is equal to A, B, naught. And y is equal to C, D, naught. So yeah, now it's it. Yeah, that's all there is. Yeah, yeah, pathetically so. Yeah. Yeah. Let's see. What are we doing next? 331. 331. Looks like I'm going to get a good nap in this afternoon. This will be great. Of course, we get the multi-sim guys and they can kick our rear end, I suppose. Determine W, X, Y, Z. All right, so I got 0, 0 going into a NOR, and this is going to be 1. The 0 and 0 becomes a 0 in the OR. It's knotted because it's a NOR. W is a 1. W, X. X is next. 0, 1. I'm going through another OR.
Are these ORs or NORs?
NORs. These are NORs. Because there's a little circle there, NOR. All right, so this is a NOR. But I can think about it as an OR followed by a NOT, right? So I should get a 1 because of an OR. I get it inverted, it's a NOR 0.
So wait, so you get 0, 1, and it gives you 1, and then it's inverting, so it's 1 into 0, right?
Yep, you got it. Yeah, that's all there is, right? No more. Yeah, that's the way I would think about it. All right, next guy, 0, 1, 0. 1, 2, 3 inputs into a NOR, and I got a Y. So the 0, 1, 0, if it were just an OR, that would give me a 1. The 1 is inverted, so I get a 0 out. 1, 1, 1, 1, 1, 1 into a NOR, and Z would be a 0 out. 1, 1, 1, the OR gives me a 1, I invert it to a 0. Alright, that does that. 341. Make the external connections to a 7404 and a 7402 NOR IC to implement the function x is equal to a naught or b the whole thing knotted. Okay. Finally, we got something that we can sink our teeth into and take a lot of time to do and use multiple colors doing it. It's about time, right? All right, so we have x is supposed to be equal to a naught or b the whole thing knotted. That's what we're trying to do. We have two chips. We have a 7404, which is an inverter chip. There's pin 1. There's pin 2. There's pin 7. There's pin 14. And then we've got a 7402 chip, which is a NOR. Okay, so this is a NOR, this is an inverter chip. And I got pin 1, and I got pin 2, and I got pin 3. This is where you should steal some crayons from your younger sister and bring them in so you can have multiple colors. And then there's a pin 7, and here's pin 14. Okay, so now we're going to change colors. We're going to ground pin 7 on both of them, because if we don't, it's not going to work. We're going to add power, 5 volts, to pin 14 on both the chips, because if we don't, it's not going to work. Okay. Then we're going to bring A into pin 1, and when we come out of pin 1, we have A naught. And we're going to bring A naught in pin 1 on that side, and we're going to bring B into pin 2 on that side, and when we come out, we're going to have X, which is going to be A naught or B the whole thing knotted. So that's how I'm going to do that. And on the chapter 1 through 6 test, which is coming up sometime, I don't know when. Oh, after chapter 6, we'll be doing that. We'll be drawing. I'll give you diagrams of the IC chips, and you'll be running wire to them. And, okay, questions about that?
So right now.
Yeah. Now there could be an intermediate step here before I implement it on the IC chips. Okay, so I could have gone, and I probably should have gone as an intermediate step. I should have probably said A is equal to A naught or B knotted. I'm going to take A and knot it, and I'm going to take B and send it through a NOR to get X is A naught or B knotted. So if maybe it'd be more clear to go through that intermediate step before I implement it on IC chips directly. Okay, so that may have been a better idea. Maybe next year I'll remember to do that first. Yep.
So, I mean, would an A double knotted just be a normal A?
Yes. Yeah,
but
exactly.
You still have to mark it as that?
Let's say that I had something that looks like that, right? So this is A, and this is A naught, and this is A double naught, which is the same as A. Yeah. So let's say that I implemented some circuit. So I got this circuit, and it's going to be A naught or B, C, or what? Or D. Let's say I got that for whatever reason. And I decide I'm going to implement this using just nans. I'm just going to use nans. That's all I'm going to do. All right, so A naught becomes a nan, like that. And now A and this side, I got A naught on that side. B, C becomes, I'm going to have to naught my B. I'm going to have to naught my C. And then I'm going to have to bring that to a naught. So that's going to be my and. And then I've got this D down here, and I'm going to OR them all together. We know that that's wrong, so I should just erase it now, right? So we'll erase that now. Okay, so this is A, this is B, C, knotted. So that's my and. And then I'm going to OR them together, so I'm going to go and do that, and that, and this, and I'm going to come in and do that. All right, so this is my X. This is going to be A naught or B, C, or D.
I just want to clarify, I don't understand any of this part right here.
That's okay, you will. What we're doing is we're saying if I'm going to only use nans, and
that's for cost effectiveness, right?
Yeah, it's for cost effectiveness. And I'm going to, so my inverter now looks like that. And my and now looks like that. And my or now looks like that. So that's what we're doing. So we remember that that's the case. That's what we're doing. So now if I want to make that, I need an A naught. Here's my B, C, here's my D, and there's my OR circuit that'll give it to me. Okay, now that I've done that, I look at it and I say, well, wait a minute here. I have two inverters in a row, right? I have two inverters in a row. I could rewrite this thing. I could rewrite this thing A, B, C, D, and I could go B, C, and go like that, and I could go over here like that. This is inverted, and then I could come into there, and do that, and this is the same X. That's the same as what I have up there. So now I've got, if I were to implement this guy with just TTL logic, and I would need an inverter, I would need an OR, and I'd need an AND. I need 3 gates, right? Well, now I've implemented with just 3 gates, and they're all the same. Okay, and from a cost-effective point of view, and that's why we're doing it because it's cost-effective. When you remove the redundant gates, you end up having just as simple a circuit as you would have if you hadn't done that. And again, the NAND gate's going to cost you a whole lot less because we build lots and lots and lots of them.
So basically eliminate, if you have 2 inverters on the same wire, eliminate both of them.
Yeah.
Because they counteract one another.
Yeah, exactly. I have
They invert back.
Yeah, I can just remove them out. Now, there are instances where these gates, we haven't talked about how quickly they do things. but they do things in the nanosecond time frame. So they turn from a 1 to a 0 in 2 or 3 nanoseconds very quickly. We may want to delay how long it takes it for it to change for some reason. And then you'd end up putting multiple inverters together just to delay the circuit. I want to delay the circuit by 15 nanoseconds. So let's say I've got a nuclear weapon and I'm blowing it up, and I want it, right? And I have some wires that are a little bit longer than other wires, and I want to make sure that all these things blow up at the same time so I can implode the uranium and make the nuclear weapon blow up. I'll put inverters in the shorter wires so that the signal's delayed long enough so that all the explosives blow up at the same time, which is what I'm looking for. Okay, and then I'd go and hire a bunch of engineers and build a mountain in Iran. Yeah, I'd build them out, I'd hollow out a mountain in Iran and put them down there and have them work on this for 3 or 4 years. And before you know it, after 3 or 4 times, 100,000 times of getting it wrong, they'll get it right. They'll get lucky. Yeah. Okay. But the fact of the matter is, universal gates and how we use them and how do we substitute in and out is something that's in a later chapter. And so we get to do that again too. So that'll be pretty cool. E39. E39.
So page 109.
Yeah, I found it. Okay, E39. Load the circuit file for section 310A. And what we're going to have is a Johnson counter. See, now you know you made it there, right? When your name is on a circuit. Okay, so all the Johnsons, they have their own circuit, a Johnson counter. And it has a waveform. And anyway, so there are no Cordoville circuits, by the way. Yeah.
You'll get there
But
eventually.
yeah, I'm thinking about it. I'm thinking about it very strongly. What I'm thinking is we have this inverter, right? And we have the and the or and the nor and the nan, and they all have certain logic things, but there are certain combinations of those that aren't being used yet. Okay, so if I look at A, B, C, D, 0, 0, 0, 0. Well, we only, we probably have to go that high, but we're not going to. So we look at A, B, C, A, I'll get it right. 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, whatever, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So we have the and 0, 0, 0, 0, 0, 0, 0, 1. We have the or 0, 1, 1, 1, 1, 1, 1, 1. We have the nor 1, 0, 0, 0, 0, 0, 0. We have the nan 0, 0, 0, 0, 0, 0, 0, 1. Okay, so now we can have the Doug. So we have the Doug 1, 0, 1, 0, 1, 0, 1, 0. So I can have that. And we can have, because we have two Nathans in the class, we're going to have the Nathan, N-A-T-N, and then 1, 1, 0, 1, 0, 1, 0, 1. So there are certain combinations of chips that aren't being used yet. So if there was some reason to make that chip and that combination, you could have your name on it. But until you sell your first 1,000,000 copies, no one's going to let you have your name on it. Yeah.
No, a NAND is an AND with an inverter.
Right, exactly.
So wouldn't the top one, if A and B were 0, wouldn't it be 1?
Oh yeah, it's the other way. And the NOR is wrong. Let's see, is the NOR right? The NOR is right. The NAND's wrong. There we go. Now you won't know that I did it wrong. NAND. All right, so NAND. 1 1 1 1 1 1 1 0. Is that better? Yeah, that's better because it's got to be the inverted of the NAND of the AND. So we have 0 0 0 0 0 1. So we got to have all ones and 1 0. But what I'm saying is that there are possibilities. There's at least 4 other possibilities of gates out there that you could claim, and it's just that anyway. Enough of that. Back to loading the file. All right, so as I recall, I put these files on my desktop on purpose so I wouldn't have to go get them. Open up, you silly thing. Problems? Yeah, problems. We can't have version 11. This is chapter 3? Chapter 3, okay, so 10A, right there, plain as day. The configuration, blah, 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 cannot be opened. You silly thing, save as. All right, so we'll go and do it different. Because clearly it worked last time, right? So we'll open it first, and then we'll go get it second. All right, so we got it there. Oh, there it is. Got it already. Now, last time we forgot to read the note. So we'll read the note this time. This is a Johnson shift register, and it generates from figure 343. Okay, so where the heck's 343? Figure 343. I got it. Page 82. I don't see any Johnson shift register. 343, wrong page.
106. Page 106.
Page 86. Yeah, page 86. There's the Johnson shift register, and it's shifting over one thing at a time, blah, blah, blah. Okay. Now, why? There has to be some reason to have this guy, right? In order to do that, and it has to do with networking things. When I do an Ethernet network, and I've got 2 computers on there talking to each other, how does one computer know it can transmit to the other?
One tells it it's ready to receive.
Well, no. It listens. If there's nothing there, then it transmits. Okay? If during that transmit the other guy listened and transmitted too, then they would collide and no information would be transferred, and no one would respond to saying that they got the data. And then at a random generated number of microseconds later, it's resent. Okay? So this works quite well. If you have 10 machines talking to each other, hey, not a problem. When you get to 1,000 machines on the same Ethernet talking to each other, then the majority of the time is spent in collisions instead of having communication being sent. So what we did is we had a thing called a token ring, which we don't use anymore because we don't put computers 1,000 together. But a token ring is something where if it's your turn to talk, you have the token and you can talk. Okay, so now we have a situation where we, if you have let's come up on this guy. So now I've got 1, 2, 3, 4, 5 computers, and this guy's got the token. It's his turn to talk. He transmits. and they transmit counterclockwise. And then he's got the token, now he transmits. Now he got the token, he transmits. So if this guy, number 1, wants to say something to number 5, it has to go through everybody else before number 5 can get it. And now number 5 would have the token, and he would transmit to number 1 saying, I got it. Okay, so, and that's what a Johnson counter would do. The person that is going to be enabled is the guy that has a 1 and a 0 by his name as you move the Johnson counter by, and now you know whose turn it is. So in an Ethernet system, there's nobody's turn. I want to transmit something, I do. And because the data burst is so short, if there's not a whole lot of people on it, it'll go through, it won't be a problem. But on other systems, it could be a problem. So if I were the Secretary of State and I had my own server, then there'd be less collisions on it than if I had a dedicated Secretary of State server in my office that was top secret, that the hard drive was removed on every night when I went home and put in the vault. Okay, so that's anyway. Anyway, so what I'm saying is that a Johnson counter has an application, it has multiple applications, and so we use them. Well, back to the multi-sim thingy. Thank you very much. Get out of there. Oh, now he did it. Oh, well. Cut out the talk. All right, there we go. Now we got that. That's up. File, open, desktop. Where's the desktop? Test gen? No. Oh, where's the multi-sim? Come I don't see it. What?
I just saw it a minute ago before you went to desktop.
Recent places. Factory talk authorization, Doug Cordoville, network. How come they're not all there? How come I'm not coming down? Aha. Outsmarted the computer. This is a Johnson-Schiff waveform generator figure, blah, blah, blah. It illustrates there with A and B input to a AND gate. Double click on the logic analyzer, turn on the power, and examine the waveform. The top waveform is the clock pulse. The middle waveforms are A through D, and the bottom waveform is the X output. All right, so I read it. All right, and those are the questions we want. Now, are those the same questions that are in our book? One would hope so.
No.
Okay. Is the output waveform correct? Yeah. Write the Boolean expression. What is the time width of the X waveform pulse? Measure the time. Yeah, that's the same thing. So it's just telling us how to get it. All right, so get out of there. Get onto here. So I'm going to open that up. I'm going to turn it on. Okay. So now the issue is, A, is what we're seeing correct? All right. So I got this internal clock down here, which is a clock pulse going on that's sampling these other things. That's what the red guy's doing. So there's my clock pulse going on and off. And the Johnson counter, it looks like a negative. On the negative trigger, it's changing. Now, is it supposed to change on the negative trigger? Okay, so back to page 83. 86. And we see the Johnson counter is in fact changing on the negative trigger. When the clock pulse goes down, it comes on, everything moves over. So the Johnson counter is correct. Now the issue is the output X correct? Okay, the output X is, what is it? It's coming, oh wow. Coming from B and A. All right, so it's coming from B and A. So when B and A are both high, which starts right there, it's going to be high. And it stays until B and A ceases to be high, and then it goes down. So the answer to the question A, okay, so this is E3, 9A, yes, it is correct. B, write the Boolean equation for X. X is equal to AB. Both A and B have to be high in order for X to be high. And C, write.
Wait, we just did B?
We just did B, yeah. Yeah, that's all there is, there ain't no more. What is the time width of the X waveform pulse? All right, so we have a thingy here that we can move over. See if I can grab it. Grab the thingy. All right, you're not going to let me grab you. Move this guy someplace where I can see him. Okay, so how come I got a T1 and a T2? They're probably both in the same spot. So what I'm trying to do is grab it with my mouse and move it over. Oh, there we go. So I'm moving the, I don't know which one that is. Okay, that's T1. So I'm moving the T1 over to where the X guy starts, and then I'm moving the T2 over to where the X guy ends. And I used to have it just right, and now I don't. There we go. Perfect. Is that perfect? And then I see that the difference between T1 and T2 is 6.057 milliseconds. 6.057 milliseconds. 6.057 milliseconds. What is the time width of the X waveform pulse? Ta-da! We're done. That's all there is, there ain't no more. But I can move my T1s and T2s around and find it.
So wait, is class over now?
It would appear so, yeah. We ran out of things to do, and we don't go to chapter next until till tomorrow. Yeah. Now remember,
Tomorrow?
well, next class period. Remember, Monday is a holiday, and don't come to school. If you're living the dorm, don't forget to feed yourself.
What happens if I'm feeding myself what?
Don't forget to.
Oh, is there no like, is the student center not open on Monday?
I don't know.